basic idea of interrupt. Now, one point is that, of course, it is contributing to the worst case execution time. Another thing is that when totally implementation point of view, when we are going to implement these type of programs, you can see you have two parallel executions, two concurrent executions, and there you have this timer count value. Now what is going on? This timer count value, initially this main program is writing some value, and this timer count is getting decreased. See, timer count is equal, when it is not equal to 0, it is getting decreased by 1. That means timer count is a particular value. It should be stored in particular location so that both of these programs, both of this code snippet, they can actually get access to it. That means this is this timer count variable. If we think now in terms of a variable, this is a shared resource. This memory location is need to be shared between these two, or maybe many more sub programs, sub functions, so that if required they can actually read or write that value. Now when we are talking about this shared resource, this is a very critical issue, how we are going to handle this shared resource, and what catastrophe may be incorporated if we are not handling them properly. So we will see a practical example about this shared resource handling and how that may lead to some catastrophe. But before that, this is about the interrupt concept. I think now it is quite clear. You can go through it. You can identify the states of the interrupt and when it is inactive, when it is active. Similarly, when your main program is active and inactive, and based on that, you can actually identify the instruction sequences. Next, we are talking about another typical scenario or another typical caution we should consider whenever we are writing any embedded software. Now we know that based on this is another example, you can go through it by your own, but for that example, you can see when you are executing this main program, this is basically gradually executing these programs. This is one add listener program, update program, and so on. So when we are going to actually complex practical specification, we can just take a simple example that we may require. You have shown whatever implementations you have done, maybe your programming data structure or basic level courses, that these type of requirements may appear. That means you are writing one function, and inside that you are basically calling multiple functions. So when we are actually following these type of writing, code writing in our embedded software, we have to check how much it is possible or how much it is acceptable. The reason is that for that, why this can be very dangerous or very cautious. We should take extra caution to write in these type of codes. We can understand with an example, and for that we have to understand the concept of program stack. Program stack means what? It's very simple. When you are writing a function, when you are executing that function or when you are loading that function is during execution, it is basically assuring a space within a particular memory location in your processor, and that is called your program stack. So what is a program stack? Basically nothing but a memory location, a storage you can think. And what do we store in that program stack? The variable, whatever the variables we are using in that particular program, and if it is calling some other program, then that other program, we have finished the execution of that particular other program, then where will I return? That is the return address. That means let's take the example A, this function. It is calling this A, B function, calling the C function, and then it is coming back to a particular address where it is writing this instruction, this return 0. That means once it completes the execution of B and C, it should come back to this location, to this address. So this return address need to be specified within the particular frame of this function. That means here you can see that this is your memory where you are gradually allocating for this program. You are allocating this is your program stack, and you are actually allocating spaces for your whatever functions you are calling. This is for frame for main, and from main, if you see this one, in this main, when you are calling A, for some frame for A or space, we can say space for A is getting allocated. Next, A, if you are calling like this, A, B, C, frame for A, then frame for B, then once B is getting executed, B is complete, this free, you are returning your program counter or your execution states from B is complete, then again the counter is coming back to frame of for A, and then so on. Again it is calling C and so on. So this way, when you are executing this function A, then it is calling B, allowing some place to be allocated for function B, and then when B is complete, again this part of frame is free. Again when you are calling C, this step, again it is allocating some space for C. So this way, whenever the idea is that whenever we are calling some function, some space need to be allocated in the program stack, and that way we are actually, based on our function call, we decide what will be our stack frames. Now, why it is important, why we are talking this so separately when we are talking about embedded software design? The reason is that in case of embedded software design, if you remember that after modeling we are going to the implementation, and there we have a concept of processor. In that processor we are implementing our code with some, implementing our requirement with some set of instructions, and for that we are using the memory added to the processor. Now when we are talking about embedded processor, initially maybe from day one, everyone is telling that one critical requirement is it is restricted memory, like restricted deadline. We have to work within restricted resource. That means our memory is very limited. So now you can understand, if we choose our different types of programming techniques, how you can affect how we are allocating the memory. For example, let's take this one. We are computing this value, n factorial. Okay, this is a factorial calculation example. I think you all know about basic C code, maybe in both way, recursion and non-recursive way. These are two ways how we can actually compute this n factorial. Here you can see, if we are going just by iterative step, not any recursive step, we are just taking a for loop, and there we are computing this result is equal to I into result. This is the main basic step of computing this factorial. Similarly, the same code I can write in recursive way, where I can write return n into factorial n minus 1. So this is the iterative way, and this is the recursive way. Now, ideally, if I just go by design, both are correct, both are proper. But when we are thinking about embedded scenario, again, if you think about the previous concept, what we have discussed, whenever we are actually computing this n into factorial n minus n minus 1, maybe n into n minus 1, this way we are computing, every time we are calling this factorial function as a sum function, as a recursive function. We are making a recursive call. That means for this each call, we are actually allocating a frame space in this memory total stack memory. That way, this number of frames in this recursive call is continuously growing, and that way it may happen for a certain limited value of n, whatever memory you have in your embedded processor, that is fine. But beyond a certain threshold, if your n is too high, you can understand the number of frames it will grow continuously, and that since n is too high, your given memory in your embedded processor may not be sufficient to handle these type of code. So that's why in spite of the fact you have done everything right, just the way of coding you have chosen in your software domain, that may affect and that may lead to some failure of your actual software execution. And the catastrophic thing is that sometimes it happens that when we write the code, we test it. These type of codes may be n with some limited values within a particular range. But when you have actually deployed your embedded software, maybe the range your client is asking or client is giving using, that may be beyond a certain threshold. In that case, the catastrophe occurs in that practical scenario, not in your test scenario. So this is one thing, that how I'm coding, whether what is my range of values so that I can choose any type of coding or not. This is very important decision maker when we are actually writing, implementing our model to our actual execution. Similarly, you can think continuing with this example, that things become worse if you actually choose, this is the Fibonacci calculation. Okay, where you can think, if you know the Fibonacci series, you know that either I can write this in this iterative way or this is the recursive way. Again, both are correct, no problem with that. But the problem is here, when we are actually going for this recursion, then this recursive call of this fib function, and that is also twice. For each fib I, you are actually making some stack frame for fib I minus 1 and again from fib I minus 2. So if your number of stack frames are increasing like this, then it may happen that your memory is quickly getting exhausted, and that is not suitable for your embedded system design. Okay, so these are the few things we need to take care. The second thing is that, or maybe I should say, first one we talked about interrupt, second one we talked about the way of coding, third one when we are talking about something small processes. Like if you remember our elevator design, one is unit control, one is request resolver, or our interrupt handler processes. One is interrupt handling process and another is my main process. So all these are small processes, and sometimes rather than creating the actual heavy process, because this is altogether operating system discussion, I cannot go much detail in that when we are creating a process and when we are creating a thread, the main difference is that thread is lightweight. So you can see if this is a process, it has these data files, registers, stacks, everything. So if you are creating multiple processes like this, you have to actually supply all this fields to actually supply all these fields to that process. But on the contrary, if you are going for threaded implementation, actually there is a possibility that these data files, that some resources can be shared between multiple threads. So that way, with the use of special resource sharing, you can understand that we minimize the amount of memory requirement while coding. So that is the advantage, because again in embedded scenario we are working in some in some restricted environment, restricted memory given to us. So that's why, of course, you can understand this threaded approach is much better rather than this lightweight process generation approach is much better than multi-process. But so this is the example how you can actually create a thread. When you are creating, it is actually differs library to library, based on what library you are using. That is, you have to create a thread. You can perform some executions within the thread, and then finally you have to get assured the threads have joined. Whatever threads you have created, they have joined, and finally you are back to your final single execution. So this is how the software, in a software language, you can write it. But the important challenging part here is when you are using multiple such threads. And let's take our example of that interrupt, where you have created your main program in one thread and your interrupt handling program in another thread. And these two threads, they both are using that particular variable that we started with, that initial value where we are setting 2000. That is the initial timer count maybe. So that is a shared resource. Now, if it happens that your multiple threads are continuously using that, writing that, and next one again it is writing that and taking the values, I mean, without implementing them in a proper way, that may lead to catastrophe, because multiple threads without any proper shared resource handling technique may read not updated data. That means maybe a thread, sometimes it is updating the data, and in between another thread, it is reading the previous old data, and it is continuing its execution based on that. So that is the challenge, and to solve this challenge, one solution is this mutex solution. Mutex means we are adding a mutex lock to a particular variable or a particular resource. If one thread, let's say thread 1 is starting to access a resource, maybe R1, it starts to put the lock on to that particular resource. Once the thread completion is done, then it will release the lock, unlock the resource, and then only another thread can actually access the shared resource. So that means there is some concept of locking and unlocking the shared resource, and that is called the mutual exclusion. That is, especially it is mainly important when we are writing to some shared variables. Reading is all are reading, then that is okay. No need to think much about it. But when there is a concurrent reading and writing requirement, then that time this mutex or mutual exclusion implementation is a very important requirement. Now, with this, I will give a practical example that is also done. Let's say, I mean, this will show you, maybe not only for your exam purpose, this discussion. It's quite advanced topic, but just to give you the idea that in spite of the fact why this embedded software design we are reading separately, and why it is so much challenging. That means what are the steps of implementation you have, in spite of the fact you have done them properly, correctly, still there are some abrupt scenarios occur, some unpredicted scenarios may occur that may lead to some catastrophe, and that may lead to a scenario where a normal execution, normal operation of your embedded software actually getting meaningless. It cannot proceed actually. Now this is one example. This is one practical scenario where this not so proper, I should not say that is a wrong implementation, that is checked, properly tested implementation, but some care was not taken in this case of mutual execution or thread level execution. And that's why that lead to a catastrophe to this Mars bound Pathfinder mission spacecraft. So it was occurred in 1997. The Mars-bound, this is a spacecraft mission, that is Pathfinder mission. Maybe you can search in Wikipedia also and you can visit. That was the example how some minimal change, minimal, what to say, negligence in embedded software design may go wrong to a long way. So what happened here? You all of you have already read that Artos task allocation and task, task preemption concept. You know, right? So there you know that what happens in general, there's a concept of priority and there's a concept of preemption. That means when there's a low priority multiple task, they can execute one by one. But when any high priority task come into picture, so that high priority task can actually preempt the low priority task, and at that time, this low priority task should wait for the completion of this high priority task, then it will start the execution. So this is the general concept. This was implemented and still till now this we follow. There is another added challenge when there is the concept of sharing of resources between this high priority and this low priority task. Okay. So what will happen if this is a high priority task and this low priority task, both are sharing some resources, then if and at that time when this high priority task is actually entering in the system, if that low priority task is actually locked some shared resource, like if it is working with some shared resource, then this preemption is not possible, because preemption is only possible when this low priority task will come out of this blocking stage. Clear? That means this if this low priority task in this blocking some shared resource, that shared resource is shared with this high priority task, then this high priority task cannot preempt this low priority task. So in that case, there was some high priority task in that Mars-bound Pathfinder. This low priority task was sharing some resource with this high priority task, and that high priority task, when came into picture, it was holding that resource, that is in mutual exclusive condition. That's why this high priority task had to wait for completion of that particular working with that particular shared resource. In between, what happened, that was actually a flaw of design. Some medium priority task came into picture. Now this medium priority task had no, dependency, resource related dependency. That means there is no common resource that was under mutual exclusive state with this low priority task. That means low priority task and this medium priority task, they were totally independent. That's why this medium priority task preempted by rule. It just preempted this low priority task and completed its execution. Now, due to some flaw in the design, what happened? Not only single medium priority task, multiple such medium priority tasks spawned in the system. And for that, what happened? That low priority task was waiting for this medium priority task to complete. And this high priority task again waiting for this low priority task to complete and release the shared resource so that it can actually preempt and can execute and complete its operation. But since this medium priority task, multiple numbers of such tasks actually stalled this low priority task. So what happened in turn, that this high priority task also got stalled and that way, it was a critical task required for this for actual processing of this Pathfinder mission, and that also got stalled, and that missed the deadline. Since it is a high priority task missing the deadline, it was missing the hard deadline. So you can understand how that leads to actual catastrophe to this Pathfinder. So this is one example that in spite of the fact the rule was said how this shared resources can be handled, but rule was not set of these particular typical scenarios where if some lower, not so lower, some medium priority task is coming into picture. So after that, the for next with this experience, researchers what they done in future, whenever this type of sharing of resources, these concepts came into picture, one typical rule was said that whenever any task will enter in this mutex handling scenario, like we'll be working with some shared resource, it will automatically take the highest priority so that no medium priority can actually preempt and take the time, I mean delay any high priority task. So that scenario is called priority inheritance. So this is one example that we should remember, that in spite of the fact we are actually taking the advantage of threads, we are actually handling them in a lightweight memory scenario, but there are typical some added challenges when we are going for this thread concept and when we are going for this shared memory concept. Okay, so this is the part I wanted to talk to you. And the next one, deadlock. I think deadlock we have already discussed when we talked about the safety net, and we have checked the liveliness of our model or of our specification. So these are the few points that we should check. Not only just direct modeling, just not only direct implementation, but also some added features with experience. Actually, we understand that these features also may also, when in spite of the fact we are doing everything correctly, these features may also affect our actual implementation or may lead our embedded software design to an absolute failure. Okay, so that's all. I think it's already 5:30. So is there any question? Is there any question? See, you go through this part. Okay, I think Banibrata already joined. Banibrata, are you here?
Yes.
Yes, he already joined. Sorry, I have taken some part of his class. So if you have any question, that you can mail me. You can write in this box. Maybe I will try to explain it later, or I will try to maybe add some added video. Okay, recorded lectures again if you have any doubts, and I will answer your questions. Okay. Thank you.
You need 5-10 minutes. Do you need or?
No, if they have any question now, then I can answer. Otherwise, it's okay. I can.
Okay.
I think they are not having any question now. They are not asking anything. Okay. Then if I'm telling the students, if you have any, go through the lectures, whatever questions you have in mind, then you just post it in the chat here, or you can mail us. Then I will try to answer, maybe with some recorded lectures or maybe sometime later. Okay. Thank you, Bani Prado. I'm leaving.
Yeah. Okay. Thank you. Okay. Okay. So good evening, all of you. So we are meeting after a long time. So obviously in online mode. So you can hear me properly, right?
Yes, sir.
Okay.
Yes, sir.
Okay. So previously we have discussed the module 3 with you, right? And you know that by this time we have completed 7 modules, and today we will start the module 8. And so by this almost by this time you have got wide exposure in various aspects of our embedded control as well as software design point of view also, right? So you have been acquainted with starting from our this microcontroller, then this control aspects, then how to write the corresponding pseudo code for the controller design, that software development, then how to write it in finite state machine form, and all other different aspects from software design or modeling point of view we have been already acquainted with. So today let us start with this interfacing aspects. So how we can interface if we want to develop or design a complete embedded control system. So then how the actual hardware things will come into the pictures, and how we can basically this interconnect with each other or interface with the microcontroller systems, right? So let us start our today's module, and hopefully so today, tomorrow, and next week I will take, and uh, so mostly you just be prepared, and from the because we have very few classes left. So please follow the class as soon as it is going to be completed, or immediately whatever question comes into your mind during our discussion or during the class, please clarify it, because we may not get that much time later on. So please don't hesitate to ask questions, and mostly be prepared with each day's class in the class itself, and mostly on next Friday we may conduct a test on this module. Okay, so let us start that. So please prepare yourself in that fashion. Okay, okay, let us start. So you can see my screen also, right? Hello?
Yes, sir.
Okay. Oh, fine. Okay. So let us start our module 8. So you see, you have been acquainted with the microcontroller programming, that what is the basic microcontroller architecture at the very beginning, right? So which is a system. Then inside that we have the memory, mostly for storage purposes, like it can include ROM, RAM, hard disks, drives, etc. So these are basically the components. These already you have acquainted with. Then third component, we have the different input output devices and interface, under which actuators, blocks, displays, etc. will come. And also another important component of embedded system is software, and
So
under
your
which the
voice,
different type of
So your voice
design
is
development.
cracking. So
sir, your
sorry to
voice is
interrupt, but
cracking.
your voice.
Oh, let's see. Is, is it better now or same? Hello, is it better?
Better,
Okay.
sir.
Okay. So whenever you have some issues, please let me know. Okay. Okay. Okay, so basically these are the different essential components of the embedded system, under which the microcontroller or microprocessor is the heart of the system. Then we have the memory. Then we have the different input-output interfacing blocks, under which the sensors, actuators will come. And then we have the software, under which the different type of design, development, and programming aspects will come. Right. So these essential components you have been acquainted with. Now, today we will see that to develop or design a complete embedded control system for various intended applications, how can we interface these components like sensors, actuators in keeping the practical applications in our mind, right? So that's why among these four, so you have been already acquainted with these first, second, and fourth components. So we will now focus on these third components, which includes the interfacing of sensors, actuators with the microcontroller or the embedded system. Okay. So you have already seen this diagram, because during our initial discussion, very in the beginning or preamble class, we have given a couple of slides where we have introduced these concepts of interfacing. So you have already seen that. So here, if we have this embedded system for processing and control, now depending on our applications, it can be some temperature control system, it can be some speed control system for some motors or some robotics applications, or even you have seen the example of washing machine as well. So there, if we look at different example of embedded control system, so it necessarily it has to interface or it has to interact with the external world or the real world, right? And how it can interact? This interaction can happen by the presence of sensors, actuators, and different type of interfacing blocks, right? So you can see clearly that here, this is the embedded system, and here different type of sensors, actuators, or different connections or displays are interfaced with this embedded system. So how, what we can see, suppose this and you have we have already discussed during our feedback control in module 3, right? That in, if we look at the feedback control system, so from the sensor, the measurement data is basically measured by the sensors, and that sensor data goes to the controller. You must remember that, right? So that's why the sensors like temperature sensor, microphone, tachometer, you know, tachometer for speed measurement. Then you have the sonar, ultrasonic, position sensor. These different type of sensors, they are interfaced with the embedded system. And from the sensors, what these sensors does, they measures the physical quantity or senses the physical quantity, and those data goes to the this embedded system, right? So obviously in you can have some interfacing block which will convert the physical quantity into electrical quantity, which will be feeding back or which will be going to the embedded system, right? Then embedded system, if some controller logic we develop in this embedded system or the embedded controller, so then that controller will analyze the sensor data and it will compare it with the reference data, and based on that it will decide that what type of action it has to do depending on the applications, right? So then this from the embedded system or the embedded controller, the command goes to the process through the actuator, right? So the embedded system output will go to the actuator, and that's why here you can see switch, electric motor, speaker, they will come under the actuator, and the embedded system's output will act as the input for these actuators, right? So you can clearly see the arrow direction, that inward direction and outward direction. Okay, now you can have some bidirectional data as well. So some embedded system needs to be interfaced with another embedded system depending on my application, or even it has to be, it might requires to interconnect with some computer. Then the display needs to be connected with this system, or also you can have some wireless connections as well for transmitting the data wirelessly to some receiver at other end, right? So this is the meaning of the interfacing, right? So here clearly we can see that depending on my applications or requirement, the embedded system needs to be interfaced with the different type of sensors, actuators, even another embedded system or display boards or wireless connections module to serve various purposes, right? And that's why we must be aware of these interfacing schemes. Okay. So you this washing machine example also we have talked about. So this is just quickly we are recapping the things what we have already discussed during our preamble for this module, and then we will gradually move forward to our actual contents, right? So this washing machine example also you must remember that that will come under the example of embedded system. So where that we have discussed earlier as well. And if we look at the components of the washing machine, that is the semi-automatic or automatic washing machine. So then we can find the microcontroller will be there, storage device will be there, then software programming, and additionally we must have the interfacing components under which different type of sensors will come, like pressure sensor, temperature sensor, proximity sensor, humidity sensor, etc. And also some actuator will come like motors. Fine. And additionally we need some input button displays, etc. Fine. So here this working principle already we have discussed earlier, but in this context we want to focus that to design or build a complete embedded control system, we essentially require the sensors and the actuators, which are very integral part of the overall system. So that's why we need to study these sensors, actuators, their principles, how to interface them, and that overall characteristics, right? So as we have already seen that basically in different applications, we cannot think of automation in today's world without sensors or actuators, right? And also we have discussed earlier that even in our human body also, we have different sensory organs which will act as sensors. We have legs, hands, limbs, which will act as actuators, right? Similarly, we can in different applications like automobile, airplane, telephones, everywhere we can find different type of sensors and actuators. And if we that if we want to analyze their requirement, so clearly we can tell that sensors provide the window through which a microcontroller system can see what is happening in the real world, right? So through the sensors, it is sensing or it is visualizing what is happening in the outside world or real world, and those different type of physical quantities is being sensed by the sensors, and that sensor data goes to the microcontroller. Then microcontroller analyze that data, and based on the analysis, it can understand what is happening outside. Right. Similarly, based on the analysis, the controller will decide that what type of action it has to do. Like it has to run the motor in high speed, or it has to glow some LED, or it has to generate some heat by activating the heater. So what type of action it has to do, that will be decided by the microcontroller, and accordingly the control action or command will be generated from the microcontroller, which will go to the actuator to drive it. Right. And without the sensors and actuators, you cannot think of the automation, right? Like if you think that if in some industries, if we want to fill the water or cold drinks bottles which are in crowds, if we want to fill them manually, it is quite tedious job. It is, and it is obviously it is very that not an efficient approach. Right. Now, if we look at that this interfacing, so basically this is the microcontroller. You can see where different type of functionalities or processing or different type of control logics or procedures is being happen, right? And it has to interface with the sensors and actuators. But the interfacing, we cannot directly connect the sensors with the microcontroller, or also we cannot directly connect the microcontroller output to the actuator, right? So in between, they need some interfacing blocks, both in the for the sensors as well as the actuators, right? So you can understand that suppose the sensor, different type of sensors can give different data, like temperature sensor, you can have pressure sensor. So those will measure the physical quantity, and some can have analog output, some can have digital output, pulse width output, whatever. So but in order to connect it or make the output of the sensor compatible with the microcontroller, which will actually process the data and which will do some control operations. So in order to make the data compatible, we need some interfacing block which will take the sensor data, then it will that convert that physical quantity into some electrical quantity. Again, you know that the embedded controller that will only understand the digital data. So again, this analog data will be converted into digital data. Then obviously you might require some another blocks as well for amplifications or different processing as well, and that data will actually be fed to the microcontroller. So you cannot directly connect the sensors to the microcontroller, rather you need some input interfacing blocks. Similarly, at the output also, the microcontroller, you know, typically it will give you 5 volt signal, right? So and depending on my type of actuator, like if you think of some DC motor, so that requires typically 12 volt, 24 volt like this. So that this 5 volt cannot drive that type of actuators, right? And also here again that type of data is also an important factor, because this microcontroller will give you digital data, but the actuator which you want to drive, that may not handle the digital data, it might require analog data. So that's why you need some output interface block as well, which will make the microcontroller output compatible with the actuator, right? So this is the data flow in the embedded system. So I hope you understood. So please let me know if you need any clarifications or if you have any doubts. Okay. So now we will see that the typical block diagram of the measuring instruments or the sensor system, right? So another thing just I want to mention. So suppose I think 2 or 3 students from this batch have attended that ECS embedded control system course as well. So in that course, we have analyzed, we have discussed in detail about these interfacing aspects, right? So obviously here, this is the concise portions of that. So they may find some similarity with that course, but here we will give the gist because this is only one module. We will be covering this whole sensors, actuators, and interfacing in this one module, that is the module 8. Okay. Okay. So suppose if you see this that block diagram of the measuring instruments, like you think of that. Suppose if you are in an auditorium and you you are using some microphone to transmit your signal to the corner of the auditorium. So you think of the big auditorium like Kalidas auditorium, right? So we essentially require some microphone speaker system, right? So because the from the stage, if you say something, so it cannot, that sounds cannot reach to every person in the auditorium, right? So in that case, what you need, suppose you have you are speaking something and you need some microphone, so which will act as transducer. What is the meaning of the transducer? So basically this transducer converts the one form of signal into another form of signal. Okay, so we know that when we are speaking or talking, so that is the acoustic signal, right? So acoustic signal, the transmission of acoustic signal, that is one factor. Secondly, we need to amplify that signal. So this type of operation like transmission, amplification, so those type of operations are difficult with the other type of signals. So that's why preferably whatever be the signal type, we convert it into electrical signal, and on that electrical signal universally we apply different type of processing, amplifications, filtering, so that we can transmit properly, right? And again, when you are hearing as a that audience, so then obviously that electrical signal you cannot hear. So that's why at the receiving end, you need to again convert the electrical signal into acoustic signal so that you can hear properly, right? So here, just that example has been shown here. So like you are speaking something, that transducer like the microphone here, so that will convert that acoustic signal into electrical signal. Then you need some sort of processing, like suppose your that signal might consist of some noise which is unwanted, so then you need some processing block. Then again you need some amplification block, so that your voice will be amplified and it can reach to the every corner of the auditorium, right? So that's why those type of processing will be required, uh, which will be happening in these blocks, and this will that those processing will be done on the electrical signal, right? And in that electrical form, mostly in electromagnetic wave form, that acoustic signal will be transmitted. And again at the receiving end, as I said, that electrical signal or this electromagnetic wave signal you cannot hear. So that's why in this receiving end, again you need another transducer which will convert the electrical signal into back to the acoustic signal so that you can hear properly at the and obviously the voice what you will be hearing, that will be the amplified version, right? Now if we typically analyze the block diagram, so it typically includes these blocks, like the input will come from the outside, and then we have some sensing element. This is the typically the block diagram of some sensors, overall sensor system, right? So then the sensing element will that raw sensing element will measure the physical quantity, like if you think of some temperature sensing, so temperature will be the input. Then you have some resistance temperature detector type of sensors which will sense that temperature. And then you need some signal conditioning element which will basically that convert the this physical quantity into electrical quantity. And then again you need some amplification block or analog to digital conversion block as well, which will come under the signal conditioning element. Then you might require to do some sort of processing like filtering up operations on that signal. So that's why you need some so under signal processing, you can include some filter operations, for example. Then finally, you have some
Hmm.
data, that data, whatever
So
to
your
show
voice is
some
not coming.
data. Yeah. Now, can you hear?
Yes, sir.
Okay. Okay, so here just we were discussing about this block diagram. So the from the sensing element, then it will go to the signal conditioning element, which will include typically the amplifiers, ADC for digital conversion, etc. Then under the signal processing block, you can think of the filter operations to remove the unwanted signals, right? And under the data presentations, it will include typically some displays or some wireless module so that you can that present your data in that proper readable form, right? And finally, from this element, you can find the output or the measured value, right? So this is the typical block diagram of the sensor system. Now, if we want to see from our embedded application point of view, that typically there are different type of measured quantities required, like and they can be categorized under this mechanical or thermal or electrical like this. So under mechanical, you can have quantity like position measurement, displacement measurement, velocity, acceleration, force, etc. Right? Similarly, under thermal stimulus, you can think of the quantities like temperature, flux, specific heat, etc. If we think of some electrical parameters, you will get the charge, voltage, current, etc. Similarly, for magnetic, you can find magnetic field, flux, and for optical, you can find the reflective index, reflectivity, etc. Right? So these are some of the measured quantity, commonly measured quantities, which you can find in different embedded applications. Right? So in order to understand the overall embedded control system applications for our that different cases or in different applications, then you need to be aware of the sensing mechanisms for some of the commonly measured quantities, what type of sensors are used for measuring these, how they work, their working principle, what are the features, main features we need to look into while choosing a sensor, right? So those type of aspects you need to be aware of. Now, if you see the data set of some typical sensor, like for example, some acceleration sensor data set, if you look into, under which the ADXL335 example we have shown here, which is made by analog device. And in this specification data set, there are different type of parameters are mentioned. Like you have measurement range, that what is the range it can measure. Then you can have how much nonlinearity is there in this sensor. Similarly, what is the sensitivity? That means what is the ratio of output, change of output by change of input. Similarly, you can have zero G bias, you have noise performance, frequency response, and so many, depending on the type of the sensor, there are different important features or parameters you need to look into while choosing a particular sensor for your intended application, right? Like suppose you need accelerometer for some measurement. Now, what accelerometer you will choose? Whether you will go for this ADXL 335 or you will go for some another device, right? So, like for this particular sensor will give you analog output. Similarly, we have accelerometer which will give you digital output, and the range, their accuracies, their resolutions, their sensitivity, their frequency response. So those different parameters will vary for each of the sensors. Now, depending on your requirement or applications, you have to choose that which sensor will satisfy or suffice your purpose. Accordingly, you have to choose that. So in order to know that, in order to understand a data set of a particular sensor, you need to be aware of different type of important characteristics. So that's why we are going to focus couple of the important features or characteristics which you need to understand in order to that understand the that characteristics of a sensor, and also in order to that judiciously choose that what sensor or which sensor can suffice your objective or purpose, right? So that's why you need to be aware of a couple of the important characteristics. So under which the first characteristics we will look into is called static characteristic. Okay, so let us look at a couple of the important static characteristics of the sensor. So what do we mean by this static characteristic? The output O and input I of an element when I is either at a constant value or changing slowly. That means here you can see this. This is the element. Element means you can think of this one is your sensor. Now, if you give some input I, it will give some output O, right? So in order to understand the static characteristics, what do we mean by that? That for a particular type of input, we will look into what is the type of the output and at what conditions we will see that. The conditions at which the I, that is the input, that is either the constant value or although if it is changing, the change is very slow, right? So in that conditions, we will look into the output, and under that conditions, whatever the features or characteristics we will be looking into, those will come under this static characteristic. Okay, so let us look what are the different type of static characteristics. So first one is called as the range. So range you all know from the name itself, right? So range means the if we look at the sensor, so then how much range it can measure. Like if I talk about a temperature sensor, then you need to understand that whether that sensor can measure 100 degree to 500 degree, or also it can measure some negative temperature as well, or whether it can measure some high temperature like boiler temperature 3000 degree, 4000 degree as well. So what is the range? So depending on your requirement, suppose if one sensor can measure up to 500 degree, then obviously you will not choose that sensor for measuring 2000 degrees centigrade, right? So that's why range is very important factor. So the input range of an element is specified by the minimum and maximum value of I, which the sensor or the element can handle, right? Similarly, you can have output range as well, that for minimum input, what is the output? That is O minimum. For maximum input, what is the output? That is O max, right? So suppose if I have some temperature sensor which can measure from 0 degree to 200 degree. So then we will call the range is 0 degree to 200 degree. Okay. Similarly, another terminology we have that is called as the span. So span means the maximum variation in input or output. So that means the example what I told, like the sensor which can measure 0 degree to 200 degree. So then we will call this. So suppose here we have this 0 degree centigrade to 200 degree centigrade. So that will be your range. And what is your span? So range will be this one. And what is your span? Span is this maximum value minus the minimum value. So 200 minus 0. So that is simply 200. Similarly, if you look at another example where range is suppose 10 degree to suppose 350 degree. Then what will be the corresponding span? Span will be 350 minus 10. So simply 340. Okay. So these are the meaning of the range and span. Similarly, next we have the linearity. So linearity, what does it mean? If you plot your output input characteristics, and if you change your input, then how the output will vary. If it varies linearly, then we will call the sensor characteristic as linear. If it does not vary linearly, if it varies in some exponential fashion or some polynomial fashion, so then we will call the sensor as nonlinear, right? And obviously linearity is our priority, because if your system characteristic is linear, then if you can calculate the slope, then for any input, you just multiply that input value with your slope, you will get the output. So you need not do any further measurements like this. Okay, so that's why this linearity is very important factor. So if the I and O lie on a straight line and the ideal straight line connects the minimum point to maximum point, right? So suppose for this case, in this plot, this output versus input, if we are plotting, then this you can see this linear that line. So if the output input relationship is if it follows this linear curve, then we will call it as linear. If it does not follow this linear curve, if it is non-linear, so then we can call it as the non-linear. right? And for nonlinear, we have to see how much nonlinearity is there. Like how much nonlinearity, if you see this curvature line, so here you can see this the deviation between this straight line and this curvature line. From the deviations, we can calculate the nonlinearity. And how typically we can do that? So suppose you can understand that what is the slope of this line? Slope is simply your O max minus O min divided by I max minus I min for this straight line, right? And if we look at this curvature line, so there you can see that it is deviating from the straight line, and where the deviation is maximum at this point. At this typically at this middle point, the deviation is maximum, and that maximum deviation point is typically used to define the nonlinearity for a sensor characteristic. Okay. Okay. Similarly, next we have the sensitivity. What do we mean by the sensitivity? This is the change in output for unit change in input. So basically, this is defined as the ratio of delta output by delta input. Okay. So what do we understand from this? That if we change our input at delta by delta amount, like if we look at some temperature sensor, and suppose from 100° to 150, this 50° change in input, if we apply, then what will be the corresponding output change, right? So that delta output by delta input is defined as the sensitivity. And obviously, if the limit tends to 0, so that delta output by delta input, we can write it in the derivative form d output by d input, which is the rate of change of O with respect to I. Okay. So slope or gradient of the output versus input characteristics. So that is defined by the sensitivity. Okay. So just another 3 terminologies with respect to the static characteristics we will discuss, and then we will conclude for today. So another is the accuracy. What do we mean by the accuracy? It is meant as closeness of the measured value with respect to the true value. Fine. So suppose if you want to measure some temperature, and if the raw temperature is suppose 100° centigrade, that is your true value, and you are measuring with some temperature sensor, suppose this is your temperature sensor, and with this you want to measure this value, and suppose this is showing your 95° centigrade, right? So then, and another sensors, you take another sensor, suppose if it shows 99° centigrade. So then you can see that this second sensor output is more closer to the true value, right? So that's why we can say that accuracy of this second sensor is better with respect to the first sensor. And how do we calculate the accuracy? So suppose generally in percentage we calculate it, and typically it is equivalent to the error. Like here 100° is the true value and 95 is the measured value. So how much error is there? In the first case, the error is 5° centigrade, and in the second case, the error is only 1° centigrade. Okay, and how we calculate the accuracy? So 5 divided by true value. What is your true value? 100. So with respect to 100, 5° error is there, and then we multiply it with 500 so that we can express it in percentage, that is 5%. Similarly, for this case, the error will be 1%. And in this context, we call the accuracy of the second sensor is 1%, and the accuracy of the first sensor is 5%, right? So we don't tell the accuracy is 95% or accuracy is 99%. Rather, we tell the accuracy for the first sensor as 5%, and for the second sensor it is 1%, right? So that's why if technically, if someone asks you that which sensor is better, if some sensor is showing 60% accuracy and some sensor is showing 2% accuracy, so obviously you will go for the 2%, because actually accuracy is related to your error value. Okay. Similarly, next terminology is known as the precision. What do we mean by the precision? It is a term which describes an instrument's degree of freedom from random errors, and it defines the closeness of the readings if large number of readings are taken. Right. So this is related to the basically repeatability of the system. So suppose if you are with a sensor, if you are measuring multiple times. So here the example is shown. Like here, if you this is your actual value and you are measuring it. Suppose 100° is your actual value, and every time you are measuring, it is coming around 90. So sometimes 91, sometimes 89, sometimes 90.5, sometimes 91.3. So likewise. So multiple times you are measuring, that multiple measurements are with around this 90 degree centigrade. Okay. And what is your actual value? Actual value is 100 degree. So what we can see, what we can say for this, the accuracy is not good because the error is almost 10%, but its precision is quite good because that the repeatably, when you are measuring repeatably, then the values are coming very closer to each other. So that's why if we consider this sensor, then we can say for this sensor the precision is very high, but accuracy is not very high. Okay. Where if to the 100, 101, 99 like this, so then we will call both the accuracy as well as the precision is very good for that sensor, right? So to visualize that, here we have shown these three diagrams. So where you can see here that multiple times these dots correspond to the multiple measurements. So here this middle one is our actual value, that is my required value, that is the true value, but multiple time you are doing the measurement and they are going around here and there. So that means both the accuracy as the precision and the precision are low. For the second case, where multiple time measured values are closer to each other, but that is far away from the true value. So that's why we can call the precision is very high, but accuracy is less. And another case can be where both the accuracy and precision is very high. Okay. And another last characteristics under this static characteristics is known as the resolutions. So what do we mean by that? Resolution is defined as the smallest change in input that can be detected by the instrument or sensor, right? So suppose you are measuring some 100-degree temperature, okay? Then you are just changing. So suppose 100.1, you are making 100.1. Then you are seeing the output. Output can be resistance or output can be voltage, right? So suppose 0.1 degree input you are changing, you are seeing output is not changing. Then you change your input from 0.2. Likewise, suppose for example, when you are making the temperature from 100 to 100.5, then you can see the output is changing from some value to some another value. So that means what is the minimum difference in input it can measure? 100.5 minus 100 equals to 0.5, and that 0.5 will be called as the resolution for the sensor, right? So that has been shown by this staircase diagram, where you can see you are changing your eye and then output is not changing, but only after certain value the output is changing. So suppose during this horizontal line, no change is there, but you are changing the input, but output is not changing. Only when you are going above this step, then only the output is jumping to another value, right? So that's why this minimum change in input, which can be detected by the sensor, that will be called as the resolution for the sensor. Okay. So so far about so we have introduced the requirement of the sensors and actuators. Why do we need to study them? Why do we need to interface them with the microcontroller for our intended applications? What are their typical features or characteristics for different sensors? What is the typical block diagram? And then we have looked into the that data sheet of a example sensor, and then we have told about the static characteristics under which the different terms like range, spans, accuracy, precision, sensitivity, linearity, resolution, these important features will come into, and we need to understand the relevance or interpretation of this terminology so that we can understand the characteristics or features of a specific sensor, and we will also understand that whether that particular sensor, by looking at the data sheet and looking at these specifications, we can understand whether a particular sensor will suffice our job or not, right? So till now, if you have any doubts, please let me know. Okay. So any questions so far? Please let me know if you have any questions. If you don't have any questions, so then we will conclude for today's class and then we will continue tomorrow. Any question?
No, sir.
Okay. Okay. Okay, fine. So thank you. And please keep in mind that mostly on next Friday, there might be a test on this module 8. Okay. Thank you.
Thank you, sir.